I don't know if anybody out in the hall wants to come in. Do you want to alert them that we're starting? I mean, maybe they're out there for a reason. I heard vibrations, yay, but maybe not everybody feels like that. I don't know. I don't understand that, of course. Not at all. Did I say something funny? No. Okay. So how was the coast? Was it good? Yeah. It's pretty spectacular, isn't it? Yeah. And you feel ready for another week? I don't see a lot of enthusiastic head nodding. It's kind of like, It was a pretty intense week last week, I think. Yeah. Okay, maybe everybody's here who wants to be here. So I'll go ahead and start. Okay, so remember this is the bit about vibrations. Remember what we're trying to do is build a theory of parametric polymorphism for system F. And the idea is that we're going to extract the vibrational essence of Reynolds construction. And then we're going to use that to build some general models. And so we've already had lectures 1 and 2, and today we're on lecture 3, which is the lecture in which we don't do anything. Okay? What's happened? Okay. So this is the lecture in which we are going to try to look at Reynolds construction through a bivibrational lens. So in lecture 1, we recalled Reynolds construction and took this as our main inspiration for the model that we're trying to construct. And then last time, we had an introduction to bivibrations because I can't very well tell you about, take a bivibrational view of parametricity without telling you what bivibrations are or reminding you if you already happen to know. And so today, what we're going to do is look at Reynolds' original construction, but we're going to look at it through this bivibrational lens. Okay? So remember, he worked with relations and sets, and we're going to do the same thing, but we're just going to like put on our bivibrational glasses and kind of look at it in a different way. And in that way, we're going to gear up for our generalization. And of course, the idea of a generalization is that Reynolds construction is going to be an instance of such a model, well, at least if you ignore the size issues that cause problems in the first place. Okay, so today I'm going to introduce you to a particular bivibration. It's called the relations vibration on set. And like I said, we're just going to look at Reynolds construction through that particular bivibration. Okay, so remember, the first time we saw his construction, we didn't even talk about bivibrations at all. They were just something kind of lurking in the background waiting for you. And we're going to restate the construction in those terms. And in that way, hopefully, we'll set up all the infrastructure we need for our generalization. So that's the plan. That's what we're going to do. Okay. So I need to introduce you to this relations vibration. And for that, I need to introduce you to the category rel. So when we talked about Reynolds construction on Friday, I just wrote like REL to stand for relations, and I didn't mention categories that day, right? But now I want to look at everything categorically. So I want to make this category called rel, and an object of it is just going to be a triple. So the important part here is the R. This is the relation, but a relation always comes with a domain and a codomain. That's the idea. So I think of it as a triple: the domain, the codomain, and the relation. But the only interesting part is really the relation. Okay? So these are relations on sets. So X and Y are sets. And R is a relation on X and Y. So R is just a subset of X and Y. And I think I got a little bit sloppy in writing X cross Y versus a pair XY. So hopefully you'll just read those interchangeably. Okay, so what's a morphism in this category? Well, a morphism from one object, one triple, to another triple is just a bunch of maps. So I'm going to map X prime to X. So I'm going to go between these two pieces using an F. and I'm going to go between the y's, the y prime to y, using G. But I'm not going to take any pair of maps, right? I'm going to take the maps that map things that are in R prime to things that are in R. So it's a pair of maps, but I want to map related things to related things. Well, we've heard that before, right? That's the essence. We want to map related things to related things. Okay? And in particular, every set X has a distinguished relation called the equality relation. And it's just what you think it is. It's the pair of things that are, equal. Okay? But what you should notice here is that this equality relation can be extended to an equality functor, and it goes from set to rel. So it goes from a category of sets to the category of relations. Yeah, this category that I was just telling you about. Okay, so that's what it's going to do. Okay, so we're going to make a fibration that goes from rel to set, but I've got an equality functor that goes from set to rel. Okay, so what's the relations fibration on set? Well, remember that a fibration is just a functor. That's good for talking about substitution. Okay, so it has those Cartesian morphisms that do that nicely. So it's just a functor. It's going to go from rel to set cross set. So here I'm looking at heterogeneous relations. So relations over sets like, let's say, x, y, right? So if I have an object, a triple, x, y, r up in rel, I'm just going to map it to the pair of things it's over. Okay? And if I have to tell you what happens to morphisms, so if I have a morphism, fg, so remember that that's going to map the domains, and it's going to map the codomains, but it's going to map related things to related things. I'm just going to send it to itself. So that's what my fibration is going to do. Okay, so now I have to, that's just the functor part. I have to convince you that it's a fibration. So I'm not going to do this in detail. You can do it in detail in the exercises if you like. But this is a fibration. I'll try and say a little bit. So what do? First, I erase the p's. Then I'm going to write a new p. Actually, I'm going to write it as r. So what do? To be a fibration, I have to show you I've got a Cartesian morphism for every choice of r. That's maybe over x cross y or xy. And if I take a morphism here, then I have to make a morphism here that's over this one and has this property that if I try to factor, if I have something whose image factors through this map, then I can factor, right? So in order to tell you what this morphism is, I'd better tell you what its domain is. And we were writing that before as, well, you take the map down below and put a star and put the choice of the codomain object. So I have to tell you what that is. So that's what I've done here. It's just all the things down here that map here. So it's it's like the pre-image, right? Okay. And what about the Cartesian map? So remember that the maps are just maps down here. So I'm just going to take itself. So certainly this is over this because what does my fibration do? What does my functor do? It maps this just to itself. So I've got something that at least is plausible. And then you can check that it has this factorization property. It does. Okay? So I have Cartesian maps. And it's actually an op fibration, so I also have op Cartesian maps. So for that, I have to play the game kind of the opposite direction, right? So I have to, someone will be unhappy if I erase, right? Okay. So, sorry, Edwin. So what do? So for op Cartesian map, I start with an R. That's over an x cross y. And I have to play the game a little bit differently. So I take an FG down here. And did I go from x cross y? Okay, I did it this way. So I take an F cross G down there. And I have to produce the op Cartesian map. So I have to tell you what its codomain is. And that was the notation I was using for the codomain. So I'm going to take this set to be the set of forward images. That's what I've written up there. I'll come back to it in a minute. And I'm just going to take the map to be itself again. And then you have to check that it has the correct factorization property. Okay? So so this is the forward images. So I take, well, I think I can do this here. So I actually take this set to be the set of forward images of things back, well, over here, related things over here. Okay, so I've got this bifibration, this relations bifibration. All right, and that's all I've said. So, yep, got a bifibration. And I'm going to write rel xy for the fiber over xy. So remember, this is the set of the collection of all the things that map to xy via the fibration here. Okay, but that forms a category. All the maps over the identity. Okay, so let's have a look at Reynolds' semantics of types vibrationally. So you already know all about it in a non-vibrational, from a non-vibrational point of view. But remember that the idea was that Reynolds didn't just make like a set semantics and then a relation semantics, but we saw that he tried to do that, but actually that those semantics were really interconnected, right? So we don't just have like one semantics, we have this interconnected semantics. Because remember that when we were interpreting types, remember how for variables we had complete independence, and by the time we got to arrow types, we had the relational interpretation dependent on the object interpretation, and by the time we got to for alls, there was all kinds of mixing of levels. Okay, so we have these two interconnected semantics. And we also had this property. So we had this nice property that if I have a bunch of relations, Ri, that are over some sets xi, yi, then if I look at the interpretation of a type in a context that interprets all the variables, the type variables in delta using these Ris, then I get a relation that's between the object interpretation of tau with respect to the domains and the object interpretation of tau with respect to the codomains. So we had that nice property. We built it in at the variable level, and then we propagated it up. Do you remember that? So we can look at this from a vibrational point of view. So let's just have a peek. So what are we saying? So this statement, the one that we just talked through, it says this. If I look at the relations vibration on set and let U stand for that, then I claim that every judgment, right, every well-formed type is going to introduce a fibered functor that goes from, well, cardinality of delta, where delta is the type context here, cardinality of delta copies of U, well, discrete, so I don't have any morphisms except for the identity morphisms, into U. So why is this statement saying that? Well, okay, what have I got? I should have a relational interpretation of tau, and I should have object interpretations of tau, but remember that the relations vibration is over set cross set. So here's U, it's going from rel to set cross set. And what I'm saying is that if I start over here and take a whole bunch of relations, like delta, cardinality of delta many relations, that are going to interpret my type variables in delta, right? That's this piece right here. So I've got all these R's, I've got this R bar, and I look at this thing with respect to R bar, and then I look at what it's over with respect to the relations vibration. Well, what I'm saying is it's over this pair, right? I've got a relation between these things. And that's exactly what I'm saying here. If I look at these, this R bar, and I look at what happens under sort of delta many, cardinality of delta many copies of U, I get all the domains, all the codomains. So I look at the object interpretation over all the domains and the code and all the codomains, and that's, well, there's the object interpretation with all the domains, there's the object interpretation with all the codomains, and I get to the same place. So this is saying the same as that. So what we're saying is every time you have a type, you interpret it as a fibered functor. So that's pretty nice. That's what Reynolds did. Yeah.
Why is it cardinality of rel?
Oh, sorry. So that's a good point. So these bars are cardinality bars. This is discrete. So yeah. So yes, always good to mix up your notation. Right. So this is just standard, so I didn't bother to change it. But you're right, I'm using the bars in two completely different ways. So this is cardinality of delta. I could have put like a hash or something maybe. And this says I'm looking at the discrete category rel, so all the morphisms are just identity morphisms. Yeah. Yeah, but thanks for pointing that out. I meant to mention it. Okay, and why are we using these discrete categories? Well, remember Reynolds' construction? He didn't actually say anything about the action on morphisms, right? He just gave interpretations of types. He didn't like give interpretations of any maps between types or anything like that. Okay, what about the identity extension lemma? Well, we can take a vibrational take on that as well. So remember, the identity extension lemma says this: if you have a type and you interpret it in a context that has a whole bunch of relations, right? So we look at the relational interpretation, and you interpret that with respect to a bunch of equality relations. So basically, you interpret every type variable in your type as an equality relation, and you propagate that up a type hierarchy to see what you get at the type tau. What do you get? The identity extension lemma says, oh, I just get the equality relation on my type, but oh yeah, well, I have to interpret the type variables at the at these sets in which I'm taking the equality relation. Okay, so that's what the kind of standard version says. Well, we can take a vibrational point of view on that too. So if I look at a type judgment, then this statement is the same as saying that this diagram commutes, or in other words, saying that this equality holds. So if I start over here with a bunch of relations, and I look at the relational interpretation of tau with respect to them, right? So, sorry, that's not right. I want to start here. First, I want to start down here with a bunch of sets. I want to form the equality relations on each of those sets. So that's what I've done here, right? Started with a bunch of sets, x1 through x cardinality of delta, form their equality relations. So now I'm up here. Now I interpret tau with respect to those relations. So now I'm over here. What do I get? I get the same thing as if I started down here with those sets, interpreted tau with respect to those sets, and then formed the equality relation at the top. So going this way is this side, and going that way is this side. Okay? And this is just saying that, and these guys are the same. This is just written compositionally, and that's written pointwise. Okay, so identity extension lemma, I can also think about it in terms of vibrations. That's pretty cool. But now we have the hard part. Okay, here comes Reynolds' abstraction theorem. Remember, this is a theorem that says related things go to related things, right? So if you have a bunch of types that are related, a bunch of terms that are related, and you have a type and you want to interpret it, look at its relational interpretation, you should end up somehow mapping related things to related things. So let's see what happens. So Reynolds had given these relational interpretations for terms, and we had the property, as you saw before, that the relational interpretation of a type with respect to a bunch of relations is over, or maps to, by the relations vibration, the pair that consists of the object interpretation of that type with respect to the domains, and the object interpretation of that type with respect to the codomains. That's what we had before just a couple slides ago, and we also had on Friday. And then we had this abstraction theorem. So I've just written it in compressed form, but it's exactly the one you saw on Friday. It says if you take some types that are pairwise related in the sense that there's a relation between them, and if you take two things, like, well, a bunch of A bars and a bunch of B bars, that at least are potentially related by the domains and codomains of these relations. And if you look at the judgment that needs that many types and that many terms, and if your things that are going to stand in for your terms really are related, then if you look at the object interpretations of the types with respect to, well, the domains and the codomains and the things that can be related by the domains and things that can be related by the codomains, then you get things that really are related. So this was our interpretation. This was our requirement on the relationship between the relation interpretations of types and the object interpretations of types. And this is exactly the theorem that we saw Friday. So that's a traditional statement. So basically, if I look at the interpretation of a type, and I apply to related types, and I apply to related terms at those types, I get things that are related. That's what it says, right? Well, I can see that vibrationally too. So here's the picture. I start off with exactly the same typing judgment, and it split across lines here, so sorry about that. And the way that we state the abstraction theorem vibrationally is we say, well, if you look at the interpretation of a type, it's just a fibered natural transformation. So we talked about those right at the end last time. So how does that work? Okay, so I want a fibered natural transformation between the context and the type itself, right? Because somehow I have to map these terms are going to map context to types. So I'm mapping context to types. And I claim that I've got a fibered natural transformation. Okay, so what about this map between contexts and types? Well, I've got something that's in it for sure. If I look at the object interpretations of my term, and I pair them up, then that's going to be one piece of a fibered natural transformation. And if I look at the relational interpretation of that same type, that's going to give me another piece of a fibered natural transformation. And here they are. So I've suppressed all the deltas in the picture. But this part here is this. And this part here is this. And I've tried to draw it in this suggestive way where I've got a fibered functor, and I've got a fibered functor, so this one and this one. And so I'm looking at the relational interpretations, and I get a kind of part of a natural transformation on the relational parts. And down here, I've also got the context, but now I'm looking at object interpretations, and I have to pair them up because rel is over set cross set. And down here, I look at the interpretations of tau, but I'm going to look at two copies again for set cross set, and I'm also going to look at object interpretations. And I get another piece of a natural transformation down here. So I get one here at the relation level, one down here at the object level. This is the one at the relation level, at the object level. And this here is the one at the relation level. And they're just right over each other. Okay? So that's the picture that I have. It's not, I think, at all clear original, at least if you just first look at it, why this is saying the same thing that Reynolds said. So on the next slide, I'm just going to unpack this a little bit, okay? So we can see that we're actually saying the right thing. But the slogan is types are interpreted as fibered functors, and terms are interpreted as fibered natural transformations. Okay. So I know that in the first week there wasn't a lot about semantics of system F, but often if you're going to interpret system F categorically, a type would just be interpreted as a functor, and a term would just be interpreted as a natural transformation. But we don't just want any old interpretations here, right? We don't want any old model. We want a model that has this property of sending related things to related things. So we don't want to make like, oh, here's an object interpretation. It's completely independent of this relation interpretation. We don't want that. We don't want to have like two parallel semantics. We want to have we want to reflect this kind of interconnectedness. But still, essentially, types are going to be interpreted as functors, and terms are going to be interpreted as natural transformations, but now they're going to be fibered, and that's how we're going to talk about the connectedness. Okay? So it's the same situation as in the standard case, except that everything's fibered. So that's the slogan, right? So instead of saying, oh yeah, types are functors, terms are natural transformations, you just say fibered everywhere. Okay, so now you can all go to sleep. So you know the punchline. That's it. All right, so let's unpack this. Okay, so the domains here are discrete. So the domain, we're looking at the discrete category on rel, so all the morphisms are identity morphisms, and down here we're looking at the discrete category on set, so all the morphisms are identity. So that means that as soon as I make a map, I'm going to end up with a natural transformation because I don't remember every kind of component of a natural transformation has to be a morphism, and the only morphisms I have are identities. So as soon as I make a map at all, I know that I've got a natural transformation. So my domains of my interpretations of contexts and types are discrete, and that tells me that my interpretation of my object interpretation of my term is going to be, well, vacuously, a natural transformation between the context and the type. So between this context and the type. Same reasoning tells me that my relation interpretation is going to be a vacuously natural transformation between the relational interpretation of the context and the relational interpretation of the type. And the fact that I have a fibered natural transformation is telling me that the relational interpretation is over the pair of the two copies of the object interpretation. Okay, so that's this. The interpretation here is over two copies of the object interpretation. Okay. So what that means, if we unpack it, is every component of the relational interpretation at a particular collection of relations goes from the context interpreted with respect to those relations to the return type interpreted at those relations. And that has to be a morphism over this pair of object interpretations. Oh, but the relation interpretation has to be over the pair of object interpretations, and my relations are all over these domains and codomains, which I've by convention been calling x bar and y bar. So what does that mean? That means that I have to go from the object interpretations interpreted with respect to the domains and the object interpretations interpreted with respect to the codomains to, well, the same thing over here, but now instead of context, I've got the return type, right? Okay, but remember the relations vibration on set. Remember what that does. Remember what the morphisms are. Well, it's just a pair of morphisms between, it's going to be between the object interpretation of the term with respect to the domains and the object interpretation of the term with respect to the codomains, but not just any such pair of maps. It's going to be, so I've called my pair of maps this thing and this thing. Not just any pair of maps, but a pair of maps such that if I start off with things that are related in the relational interpretation of the context, I should get things that are in the that are related by the relational interpretation of the return type. Oh, well, if this is my map and this is my other map, then here I am feeding one component of the object that's in the relation, and here I am feeding the other thing, the other component of the objects in the relation, and I should get things that are related. That's just what Reynolds said. That's just what you saw on Friday. So if you go back and you look at this funny diagram and you just unpack the pieces, you end up with exactly what Reynolds said. So that's pretty neat. I don't think it's obvious at all. So if we kind of stand back and think, okay, what did we really say aside from insert fibered everywhere? What we said is that if you think about Reynolds' abstraction property, remember when I first told you about interpreting types, I said, types and terms, system F, I said we're going to give a relational interpretation and an object interpretation for types. And for terms, we're just going to give an object interpretation. Remember, that's how we started out. And I kind of said, well, you know, it seems a little bit like asymmetric. So you could say, one way to talk about what we've just done here is we've said, well, if you think about Reynolds' original formulation of the abstraction theorem, it looks like it's saying something about the object interpretation of terms. But you could also say that it's hinting at some missing relational interpretation of terms. So it's hinting at some missing structure, right? So instead of having object and relational interpretations over here for types and only like poor lonely object interpretation for terms, it's also saying, oh, there's a relational interpretation for terms over here too, right? So it's saying that there really is some kind of symmetry going on. Okay, so that's another way to read this. And so I think you can say that this point of view exposes some hidden structure, and exposing this hidden structure opens the way to generalizing his construction. And if we want to do that, then what do we have to do? Well, I'd like to work with things other than traditional sets and relations, so I want to generalize in that way. So I want to look at not quite arbitrary fibrations, but arbitrary fibrations with enough structure. And we want to talk about the identity extension lemma, and that's about equality. So if I want to talk about that, I have to have a notion of equality in these fibrations. So I need to make sure that I have enough structure around that I can talk about equality. Okay, so that's all I've said here. I want to generalize this object interpretation and relational interpretation in such a way that the identity extension lemma and the abstraction lemma hold. That's the whole point. It's not a very good generalization if the main theorems don't hold. Okay, so we want that. And that means you have to have enough structure to make sure you can set things up to even be able to talk about the things you want to hold. If you can't talk about them, they definitely don't hold, right? Okay, so that's what I want to do. So maybe pause for a moment, catch your breath. Questions so far? Yes?
So, non-vibrational model of system F equals maybe we will talk about it?
Yes.
You can't do things like the abstraction theorem.
You can. Yeah, so the question was, what if you have non-vibrational models of system F? Can you, do people make them? And the answer is yes. And the follow-up question was, well, can you talk about things like the identity extension lemma and the abstraction theorem? And the answer is yes. So I think Amal will probably talk about some other models, but you can, not only can you make non-categorical models, you can even make non-kind of denotational models, non-mathematical, I want to say like non-denotational models, but you can make operational models, let me just put it that way. So you can make models based on operational semantics. And in particular, Andy Pitts has a really, really nice paper from about 2000 where he makes a nice operational model. Okay. Yes?
So, is it kind of a coincidence, correct me if I'm wrong, that this vibrational treatment lets you operate in categories other than set? And you would greatly limit that one of the advantages.
Yes. So the question was, does this kind of treatment allow you to work in categories other than set, or with, I could say it slightly differently, other vibrations than the relations vibration on set? And the answer is yes. And yes, that is one of the advantages. This will become a little bit clearer in a minute, but if you kind of, if you think about the base category of your vibration, so your object, the place where you're going to do your object interpretation as giving you like a standard interpretation for system F. And you think about this relational level, the place where you do the relational interpretation. If you think about that as giving you notion of relatedness, then you can vary the normal interpretation, the standard, the object interpretation. You can vary your notion of relatedness. If you change the vibration, you can change the relationship between the standard interpretation and the relatedness interpretation. And so you've kind of got like these three moving parts, and you can wiggle them all around as long as you have, maintain the structure that you need in order to have the nice properties you want. And so now suddenly you don't just have a model, but you've got like a whole framework for models. So that is exactly the point, yeah. Okay, so how about these more general categories? How about these more general vibrations? So they are called relations vibrations. So if you go back and think about the relations vibration on set, the one I just showed you, it arises by a particular construction called change of base. So we talked about pullbacks last time. So when I say change of base, I essentially mean pullback. So here's my original vibration U going from E to B. So this is where I'm doing my, well, this isn't quite right. Okay, so I won't say that. So here's my total category, here's my base category. I can make a new vibration by pullback. So I'm pulling back U along this times functor, and I get something over here, right? This is the pullback. So remember, a pullback is like this object with these two projections. Remember that from last time? Okay, so I'm going to call the thing I get here, I'm just going to call it rel E. So it's not so don't think like set relations, although that is an instance. Just think some things I'm going to call relations. And they're going to play the role that relations played in our set and relations model. Okay, so relations are over base things cross base things. So like in the, if I were looking at the relations vibration on set, right, this would be rel, the thing we were just calling rel, and this would be set cross set. Okay. So, and I'm going to call that vibration rel U. I'm going to call it the relations vibration on U. So I start off with U, and I do this construction, and I can make this new vibration. And it's called rel-u. And so if this was a fibration, this is a fibration. If this was a bifibration, this is a bifibration. Okay, so you can prove that you can add that to your exercises if you want, or you can ignore it. So rel-u is the relations fibration on u. So that's just what we're going to call it. And we're going to be even weirder because we're going to call these things relations, even though they're not like the relations we were just talking about. So you just call the objects so these are categories. So you just call the objects in this category relations, because they're kind of like generalized relations. You just think of them as generalized relations. Okay, so the idea is that I want to, first of all, be able to talk about equality up here, right? So I want to say if I were to take something down here in B, could I make something that's kind of like an equality relation here? Because I want to have this identity extension property. So I'm just kind of setting up some infrastructure so that I can eventually make my interpretations and have the identity extension lemma and have an abstraction theorem that generalize the ones that we just saw through our vibrational glasses as generalizing Reynolds stuff. So I want to make the components that I need. Okay, so I want to be able to talk about equality up here. To do that, I first start off by talking about truth. So I'm going to say this at the bottom of the next slide. But over here, I have a bunch of objects down here in B. And up here, I don't have relations because they're over here, right? Relations are like between two things. But here I've got one thing. So up here, I can think of my objects in E. I can think of them as predicates. I can think of them as things that are true about, things that might be true about objects down here in B. Okay, I can think of them like that. So I'm going to make a functor called a truth functor. So something that kind of talks about predicates, about what's true about objects in B. And then I'm going to, from that, construct my notion of equality, because a predicate on a pair is like an equality. So that's the idea. What's the matter? Oh, okay, I thought you were telling me to move this direction. Okay, yes. You have to raise your hand louder.
Is there a way to, language you're looking at full like
I am.
of categories and functions?
A cat, yep.
Is there a standard way, let's say, of doing that? Or could we know exactly how rel is defined?
Well, it's defined this way.
Yeah, but I mean,
You mean you want to know, you want to know...
the object in the morphism of rel.
Well, it's going to depend on what E is, and it's going to depend on what B is. And so you mean like you want to kind of pick apart the structure?
Yeah.
Yeah.
In set, you can build the fullback, and we know how it is made, the fullback of two functions.
Yeah.
I was wondering if we know, in general, how is made the fullback of two functions.
Yes, so again, if you're in a category and you have terminal objects, right, like cat, then what you've got here is essentially triples, I guess, right? A pair of things in B cross B and an E. Yeah. So you're going to make the components from the pieces of E and the pieces of B cross B. Yeah. Okay. Anybody else? Yeah.
What's the arrow from below from to speed to B?
This one here?
Just a general.
It's time. So you give me two categories. Well, actually, it's two copies of the same category. And I'm in a category, I have to have products. Otherwise, this doesn't make any sense. So you give me two things in B, and I'll make their product and make a new thing in B. Okay? Even better than whatever. Yeah, okay. Okay, good. So this truth functor, so that's the thing I was just trying to motivate. So I need a bunch of structure in order to have a truth functor. So probably the best thing to do is just go through the slide, because then I have a picture I can keep pointing at. So let's assume, so if this is X and this is Y and they're down here in B, then I can look at the fiber over X. I can look at all the things that U maps down to X, and I can look at all the things that U maps down to Y. And if I have a terminal object in remember that each one of these fibers is a category, and if I have a terminal object in each one, first of all, I'll call the terminal object in a particular fiber just K sub whatever the fiber's over, so k sub x, k sub y. Okay, so first of all, I can define those things, and that gives me like a truth object, but I don't want just a truth object. I actually want a truth functor. So I also have to say, if I had a map, a morphism going between x and y, then I'd like to have a morphism up here in the total category as well, right? Because a functor should map objects to objects, morphisms to morphisms. So I've just told you how you map objects to objects, but I have to tell you about how to map morphisms to morphisms. Well, here, if I have a morphism between x and y, I'm going to map this kind of the backward direction, because remember that reindexing kind of reverses the direction of the arrows. So I'm going to go from ky to kx, and I'm going to call that map f star. Okay? So you can show that this is a functor. This is one of the exercises for today, is to show that if I map every object in x to kx, then I can extend that map to get a functor that, kind of goes the opposite direction. Okay? And I'm going to call that the truth functor. Okay? And like I said, that's just part of the homework. Yep.
Actually going to map to kx or something isomorphic?
No, kx should map to kx. But it doesn't, of course, it doesn't matter if we're category theorists, right? Because we just say, oh, it's isomorphic. But should map to kx. That's the idea. And you can define it so that it does. So this is what you do in the homework. Okay. All right, so once I have this truth functor, I can make an equality functor. So, okay, suppose I have a bifibration and I have all those truth functors sitting around. Oh, I forgot to talk about this part. Yeah, so the reindexing has to preserve fibertonal objects. Like I said, I can, my f star has to map truth functor for y over y to the truth functor over x if f maps x to y. So I have to have, things have to kind of hang together in a nice way. Okay, so once I have that, I can actually make something that behaves like an equality functor. So the truth functor is like talking about predicates, and the equality functor is going to be talking about like predicates on pairs. So let's suppose I have a morphism, this diagonal morphism, and I'm going to have one for every object x in B. And what it does is it just takes the object and it just duplicates it. Okay, so suppose I just have that morphism. Then if I look at, so here it is, taking x to x cross x. If I look at the up Cartesian map above delta x, then that is going to take kx, which is over x, to, well, whatever the codomain of that op Cartesian map is. We were calling that sigma delta x of the thing that you start with. Right? That's actually just like what we have here. I've got an op Cartesian map over a map, and I start with whatever domain I want, and I use sigma sub the thing down below of the thing on the right for the to name the codomain, and that's what I've done. I take sigma of the thing below with respect to the domain I chose to talk about my codomain, and that's going to be over x cross x. You can actually see that, and this is going to, whoops, come back. This is going to be my equality functor. Okay, so like I said before, I think of the things in E as predicates, and kx is a truth functor. It kind of tells you what things are true about x, so it's kind of acting like a characteristic function, like a predicate, right? And if I op reindex, I get this binary predicate. So I op reindex, I get this kind of predicate above x cross x, so I get this binary predicate, and that's a thing that's going to act. And since I'm going along the diagonal here, that's the thing that's going to act like my equality functor. So it's like an abstract equality functor. Okay? So I have abstract predicates, and I have abstract equality functors. Well, that's good, because everything's getting progressively more abstract. Right? We just want to do everything in general. So I don't want to be wedded to like set and relate and rel. I want to do everything in a very general a setting as I can, so that I can then wiggle the pieces around it to talk about any particular setting that I'm interested in. So that's what I'm trying to do. Good. So I've got a notion of equality. I have a notion of truth, which I'm not really going to use anymore now that I have equality. And I've got a very general fibration. I've got this notion of equality. Everything's looking pretty good. Okay, so I want to make some observations. The only one that is really important for us is this one. That notion of equality that I just mentioned, if you instantiate that in the relations fibration, you get exactly the notion of equality that we talked about before, right? It's just the set of all the pairs of things that are equal. Okay, so that means it's a good notion of equality, because when you instantiate to a simple setting, you want to get back the thing that you know and love as equality. Okay, so that's good. And now I'm going to just go through this slide really, really quickly, because I'm going to say a bunch of other things that are not relevant for this lecture. But I don't want to remove this stuff from the slide in case you happen to look at the slides later. I want you to have these things as like signposts. So the equality functor has some properties. It's faithful, if you know what that means. It's not always full. We only actually need a priori indexing along delta, because that's all I use to make the equality functor. But we actually, in order to look at these litmus test properties that I mentioned before for what makes a good model, it turns out to be very handy to have the ability to a priori index along other morphisms as well. So we're just assuming we can a priori index. We always have Cartesian maps for any map. And these issues aren't going to arise in the course, because the course is too short. But I want this here in case you decide to have a look at the slides later or something. You've got some signposts. Okay, so we made our observations. So let's see how we can use this to generalize Reynolds constructions. So remember, we're going to interpret types as fibered functors, and those are going to be fibered functors with discrete domains, right? Not cardinalities, but discrete domains. But they look very similar. And we're going to interpret our types as fibered natural transformations between fibered functors. That's what we've seen before. And we're going to thereby produce a model of system F, hopefully, for which the identity extraction lemma and the identity extension lemma and the abstraction theorem hold. And the model that we make is actually going to be what's called a lambda 2 fibration. And it's known that you can always soundly interpret system F in such a fibration. Now, I'm not going to show you that what we have is a lambda 2 fibration, but again, this is the essence of what we're doing, and I want to leave this in the slides so that you have this as a signpost if you look at them later. Okay, so all I really have to do at this point is tell you how to interpret types, tell you how to interpret terms, and then I have to convince you that the identity extension lemma holds in general, right, in this kind of general setting with this general notion of equality. And I have to convince you that the abstraction theorem holds in this kind of general setting. Okay, so that's where we are. Okay. To do that, I have to set up sufficient structure to be able to interpret my arrow types in system F and my for all types in system F. Okay, variables are easy. Okay, so all I'm going to do is kind of look back at Reynolds' construction, look at what he did, look at what made his construction work, and I'm just going to sort of impose those kinds of conditions anytime on my fibration, anytime I want to interpret system F there, and hopefully get a parametric model. And similarly for all. Just going to look at like what really made his stuff go. Okay. Okay. So the slides are going to get a little bit busy. There aren't very many more, but things are going to start getting a little bit more complicated. So this is probably a really good moment at which to pause. So again, the takeaway is normally if you want to interpret system F, you say, well, you kind of think like types might be objects, but remember types, they might have type variables, so you can't really think of types as objects because you also have to interpret the things, the type variables in the context. Okay, so that's why you get functors, right? That's why you interpret your types as functors. And similarly for terms, you have to interpret the term variables. And so that means that you have to map the term context to, the type context to whatever type you have as your result type of your term. Okay, so that's how you get natural transformations at the term level. And that's the standard way. But we don't want just, functors, functors at the object level, natural transformations at the object level, functors at the relation level, natural transformations at the relation level with no connection. So that's why we're doing everything this fibered way. So if you decided that you have kind of had enough and you want to tune out a little bit, the takeaway is, like I said, just insert fibered everywhere in the normal setting. Okay. If you want to go with me, there are just a few more slides. So I'll tell you, what I'm going to do is set up the structure for interpreting arrow types and for all types today, and then we'll actually do it tomorrow. Okay, so I'll give you a little bit of time to chew on it overnight if you want. Okay, so if you go back and look at Reynolds' definitions of object interpretations and relation interpretations for arrow types, the reason his interpretations work is because set is a CCC. So you remember that from Ed's lectures, right? So that means you've got products and you've got exponentials. Okay, so set, which is where Reynolds was doing his object interpretation, has products and it has exponentials, and rel, which is where Reynolds was doing his relation interpretations, has products and exponentials. So you need the product so you can interpret the context, and you need the exponential so you can interpret the arrow types. Okay, not only that, but the relations fibration that goes from rel to set cross set actually preserves the Cartesian structure. So it's not like I've got products and exponentials up here and products and exponentials down here and they don't have anything to do with each other. So the fibration is actually preserving them. And that's really important for making things hang together in the right way. Okay. So that's what was going on in Reynolds' setting, even though, it's just rel and set, and it's all kind of implicit. If you go back and look at his original paper, he's got all these things and they all have to kind of match up in the nice way. But we can really insist on this by having this functor and having it and stating explicitly that it preserves structure. Okay. And then the relational interpretation of a type is over, copies of the object, of a term is over copies of the object interpretation of that term as required by the abstraction theorem. So the way that he gets this is because of the preservation of structure. He doesn't say it this way, but that's really what's happening. I mean, he says it implicitly that way, but he doesn't ever talk about a functor. So what we can conclude, if we just kind of stand back, we can say, okay, that means that we can model arrow types, parametrically, so that they map related things to related things. In other words, so that the abstraction theorem holds. We can do that in an arbitrary fibration if the base B and the total category E are Cartesian closed categories, just like here, rel and set are Cartesian closed. So we'll just say, okay, whoops, keep doing that. We'll just require that our fibration is between Cartesian closed categories. And we'll require that our fibration is going to preserve the Cartesian closed structure. Like I said, it's just what Reynolds did, but we're just doing it explicitly. Okay? So, since that's what we want, I'm just going to give it a name. So U going from E to B is going to be called, so it's fibration. It's going to be called an arrow fibration if the total category and base category are Cartesian closed, and U preserves a Cartesian closed structure. So I'm just saying I have an arrow fibration if I have enough structure to interpret arrows, the arrow type. Okay? That's all I've said. I just said it in a roundabout way by referring back to the things we already know about from a couple days ago, from before the coast trip. Okay. If U has total category E and base category B, and B is a Cartesian closed category, then I'm going to say that rel U, remember that's the category I got. This is like this category, this is this fibration whose total category is like relations, and whose base category is like copies of the original base category, right? So we're going to say that it's an equality preserving arrow fibration. If it's an arrow fibration, so rel U actually has these properties, and the exponential the exponential in B and the exponential in E actually interact nicely with this equality functor that we have. So remember, the whole point of making this relations vibration is to model our relations. And then we made this equality functor because we want to be able to talk about equality so we can talk about the identity extension lemma and so on. And what we're requiring here is that, well, I don't know, I'm not really sure if I should say that eq preserves arrow or arrow preserves eq. Say it either way, right? They have to, these equality functor and the arrows have to interact nicely, right? So these are my exponentials that I'm using to interpret my arrow types. And they have to interact really nicely with my equality functors. Okay, and there's a paper that has some reasonable hypotheses that allow you to derive structure on rel u from structure on u. So right now I'm just saying, okay, well, let's let rel u be an equality preserving arrow fibration. But you might say, what kinds of things do I have to know about u in order to know that about rel u? So if you're interested in that, there's a paper where you can look and see some interesting conditions. But for right now, for us, we'll just say, let's say that rel u is an equality preserving arrow fibration. Yeah. This? Yeah, I require this, so I think you'll be able to see it next time, but basically I require it because that's what's going to ensure that the identity extension lemma holds. Okay, so I can't just sort of have like equality that might do really random things on arrow types, right? Because the whole idea is I want to start with, I want to take a type that might be complex, it might have arrows in it, and it might have for alls in it. And I want to interpret all the type variables using equality. And then as I kind of propagate those equalities up the relation in that structural way that's determined by my interpretation, I want to end up with an equality relation. And I won't be able to do that unless I know that equality interacts nicely with, with both the way that I interpret the arrow types and with the way that I interpret the for all types, which I'll talk about in a minute. Okay, yeah? Yeah, so my fat arrow, this is my exponential, right? So remember, the exponential is the way to internalize the humps. Yes, exactly. So that's what I'm going to use to interpret my arrow types. Mm-hmm. Okay. Okay, good. So what about interpreting for all types? Well, things get harder here, right? Because this is where Reynolds' construction kind of broke down. Okay, so I can tell you, here's something that doesn't work. Okay, so again, usually if you're interpreting system F, you say, abstracting over types is a little bit like the opposite of projecting on types. So I could insist that I have a, projecting on types is called weakening. So I could insist that I have like an inverse to weakening. So I could insist that I have a right adjoint to weakening called for all. And this is typically what you do. There's nothing imaginative here. So typically you interpret for all as a right adjoint to weakening. Okay, even if you want to have your two parallel semantics, that's what you do. So here you might say, oh, I'll just do that down here on the base, and I'll do that up here in the total category. But this turns out to be really the wrong idea, because you want these, you want your semantics to be really connected. So the naive idea: look for an adjoint on the base, to weakening on the base. Look for an adjoint to weakening on the total category. Try to link them somehow. Turns out to be really wrong. Why? It actually gives you all the functions, all the morphisms. It doesn't just give you, you're trying to make a parametric model, and you can't do it that way. So it's exactly the opposite of what we want to do. So here's what we're going to do instead. We're trying to make this like combined semantics. So we're just going to insist that we have one adjoint for the combined semantics, so for the combined for all. So we're going to say, here's how you interpret for all, and we're going to say, let's say that we have an adjoint for that for all. So not like two adjoints for two different semantics linked up, but think of the semantics like monolithically. Like it's one two-level semantics, not two one-level semantics. That's what I'm trying to say. And then we're going to insist that we have an adjoint for the combined semantics. Okay. So to really talk about how to interpret for all, I have to introduce another category, and this is related to the one that you were just asking about. Like you were asking about equality and the way it interacts with the interpretation of the arrow type. I'm going to introduce another category in which equality interacts nicely with the interpretation of for all. So the objects in this category are going to be equality-preserving fibered functors that go from rel u to the n to rel u. And this is a discrete rel u to the n because this is where I'm interpreting my context. Okay? So I'm just going to insist that everything here kind of commute with equality, that I have this nice interaction with equality. I preserve equality. And the morphisms are going to be, well, these are functors, fibered functors. So morphisms between functors are natural transformations. But since my functors are fibered, I should have my natural transformations be fibered as well. So I have this category that it's a category of fibered functors that have fibered natural transformations between them as morphisms, and they interact really nicely with equality. Okay. And that's where I'm going to interpret my for alls. And we'll pause for a moment and again notice that I've got discrete categories there because Reynolds construction never said anything about morphisms, right? It's the same reason that it's been all along. Okay, so here's the last slide with technical content for today. I'm going to say, just like I said before, that rel u was an equality-preserving arrow fibration if it had enough structure to interpret the arrows. Here I'm going to say rel u is a for all fibration if it has enough structure to interpret for alls. So what does that mean? Well, if I take a projection, so that's like weakening, then I have to have a right adjoint. So my projection is going to go from rel u to the, well, it depends. So pi n is going to go from rel u to the n plus 1 to rel u to the n. So projection sort of says if I've got like an extra variable, I can project, right? And I can project on that variable. So I go from rel u to the n plus 1 to rel u to the n. So if I look at projection here and look at precomposition with projection, it should take something that goes from rel u to the n to rel and give you something that goes from rel u to the n plus 1 to rel. And I'm insisting that the functors that I get preserve equality. They interact really nicely with equality. Okay, so I've got this map between well, this is a bunch of functors and this is a bunch of functors that interact nicely with equality. And I want to assume that this has a right adjoint. Okay, so I know that you only got a little teeny bit about adjoints in Ed's course. So I'm not really expecting that this is going to make sense in real time. Okay, you might have to kind of go and think about it and dig into it a little bit. But you got enough of an introduction that I think you can probably do that. Okay, so like I said, not two different semantics and two adjoints called for all and then somehow link them up, but one adjoint called for all for the fibered semantics. That's the idea. Okay, and well, it has to be natural, it has to be well behaved. Okay. And then the piece that we're really going to use next time is that this map precomposition with projection having a right adjoint for all means is that. So do you remember this from this kind of characterization from Ed's lectures? So that means that if I pick any f and any g and I look at the homomorphisms from f composed pi n, so that's like applying this functor to f. I go from there into G. That's the same thing as going from F into the right adjoint applied to G. Do you remember that characterization from Ed's lectures? Okay, so that's all I've said. And this is the form in which I'm going to use it. Okay, so all I'm saying is that precomposition with pi n is left adjoint to this for all. I've dropped the subscript because of naturality, but that's all I'm saying here. Okay, and this is the form, like I said, this is the form in which I'm going to use the adjunction in my interpretation. Okay. So, coming up, we'll actually, we have all the ingredients we need to construct our model. So next time, I'll construct that model. As I've already said, we're going to use relations fibrations that are equality-preserving arrow fibrations and for all fibrations. So ones that have enough structure to interpret arrows, ones that have enough structure to interpret for all. We're going to use those things to interpret arrows and for all and one variables. Okay. We'll interpret our types as fibered functors. We'll interpret our terms as fibered natural transformations because we now have all the structure to do that. Okay, so that's what's coming up next time. And as usual, I'll just end with some references. Some places where you can see requirements on U to get properties that you might want of ReLU. And then I mentioned these lambda 2 fibrations, and I said that you can always soundly interpret system F in a lambda 2 fibration, and that's in this paper of Seeley's. Okay, so you've got the references that you need. And that's it. So I'll take questions if you have any, or I won't take questions if you are hungry. Wait, he's raising his hand for you?
I guess so.
Okay. I didn't hear it.
Okay. Just want to understand the process of generalization. We started from like a set theoretic construction.
Actually, maybe the people over there can't hear you. Can you guys hear him?
No, what's the question?
Okay. Can you talk? Okay, yeah.
Okay, so we started with a set theoretic construction. Then we realized that we could account for the various aspects of it by using this ReL vibration.
Mm-hmm.
Okay.
Exactly.
And then we decided to see what we could build around in an arbitrary vibration. Is that the idea?
That's exactly the idea. Yep, that's what we did. So Reynolds' original construction, like I say, didn't work, but it was really right anyway. And if you look at it through a vibrational lens, you see that there's like a little bit of extra structure that somehow wasn't accounted for there. But once you see that, then it kind of opens the way to generalizing. And then you can say, I want an arbitrary vibration. I want to make this arbitrary relations vibration. I want to be able to say what it, I want to have like all different kinds of object interpretations. I want to have all different notions of relational interpretations. I want them to be linked in a really nice way so that you can actually make it, not just a model, but I want to make a parametric model. I want to make one of these really nice models where like related things are related things. And kind of looking, so it's a little bit like you put on your vibrational glasses and it all becomes beautiful, right? Like everything. Yeah.
The last step of the generalization is needed to get rid of the sense issues?
In effect, yes. I'm not going to do that in an explicit way. I'm just going to show you how to interpret system F in a bifibration that has all the structure that I just introduced. So that is where if my original vibration is U, where ReLU is an equality preserving arrow vibration, that's also a for all vibration. Yes.
So in the last step, for all types, were we constructing a fibered junction?
Yes. Oh, sorry. The question was, were we constructing a fibered junction? So I actually can't hear very well because I'm putting some liquid in my ear, but I guess I can hear better than he. He's facing me too, so I have an advantage. Yeah.
This is kind of an open-ended question, but there's other ways of getting parametricity. So like Sumi and Pierce looked at using encryption, sealing operations, and other people have done the same thing. Mm-hmm. And then in the context of gradual typing, Phil Wadler and other people have proposed various encodings of universal types that are strange in certain ways. So do you think there'd be value in trying to apply this methodology to explain those mechanisms too, or?
Right. So did everybody hear the question? Yeah. Okay. So the question is basically there are lots of other models, and Nate listed some specific ones, and I didn't list like a whole bunch of others because he's not still talking. And the question was, is there any value in seeing those other models through this lens? And of course I'm going to say yes, because I think again, it's not just that we can make a model; it's that we have a whole framework for making models. And if you begin to see all these disparate models through this one framework, then you see commonalities and so on. So, and also, you know, if you understand this construction, then it gives you some insight into those models. So, I mean, abstraction is always your friend, right?
I guess I was wondering specifically, like in the gradual typing world, there's been some debate about what the right mechanism is, and some of the encodings have strange properties. So it'd be really cool if you could say this encoding is weird for this reason because it because of categorical.
So, so if you are unsure, like if you have some model and you're like, has weird properties, then this might allow you to say, well, those are weird properties, but I can account for those, right? Versus those are weird properties because they're just weird properties. Yeah, exactly. So it might give you some kind of principled way of sorting out the necessarily weird properties from the unnecessarily weird properties. Yeah, absolutely. Yeah. So but there are lots and lots and lots of models, and I mean, I haven't looked at every model in existence and put it in this framework. But a lot of well-known models do fit into this framework. Like the PER model fits into this framework. And so on. Was there one more question? Yes.
So we only need that our base category has like it's these arrow variations, right?
The base. So the question was essentially, what about the base category? What does it need?
Yeah. So we just need that the Cartesian with these arrow variations. Right?
Well, so yes, we need them to be Cartesian closed.
Yeah.
And we need them to kind of be linked to the same kind of structure from the total category. So that's what you mean by
Cartesian. Yeah. Sorry.
Mm-hmm.
So like, what I guess what I'm asking is, like, what else can you choose from the set, and like, what does that tell you about the data?
Right. So what other base categories could you choose? Well, I was just saying, like, you could choose PER. So in the paper, if you look, there are, I think in the last section, there are maybe 5 different instances of a model. So one thing I want to say at the end is that it isn't just that this accounts for models that are well known, although it does account for models that are well known, which is a very good thing to, you know, that's a good property of a theory. Right? It also predicts models that weren't known. So it has like a descriptive and a prescriptive quality. So that's nice. But yeah, still for model, or some realizability models, or whatever. Okay, everybody hungry? Yeah, okay.
Wait.
Yeah, everyone just wait. Sorry, I tried to lecture, but the project got dropped in the case lecture. The lecturer wants to move Yeah, and we'd like to thank the links you provided for the future of